Imagine trying to build the ultimate bicycle, but instead of using steel or aluminum, you build the entire thing out of solid coal. It might look incredibly cool sitting in your garage, but the second the rider hits a single bump, the whole frame instantly shatters into dust. It seems obvious we wouldn't build a vehicle out of coal, sulfur, or oxygen, but why is metal our default choice for almost everything we build? To answer that, we have to look at the periodic table of elements. You can think of it like a giant manufacturing toolbox, split into two rival teams with completely opposite personalities, the metals and the nonmetals. Nonmetals, like the carbon that makes up coal, tend to hold on to their energy very tightly. This makes them great insulators, but it also makes them incredibly brittle. If you put them under the stress of a heavy, moving structure, they simply crack and fall apart. Metals, on the other hand, share their energy freely. That sharing gives them physical superpowers, allowing them to absorb heavy impacts and be formed into the tools we need every day. The first superpower is called malleability. This means if you take a raw piece of metal and hit it with a heavy hammer, it won't break. Instead, it allows you to press it flat, almost like dough. That ability to be hammered without cracking is how we shape broad, curved sheets of metal that eventually become the fenders or the frame tubing of a bicycle. The second superpower is ductility. If you take a piece of metal and pull it from opposite ends, it will stretch out into a long, continuous wire without snapping. This is how we create high-tension cables required to operate the bike's brakes and shift gears. We are literally pulling the metal into shape. Because of malleability and ductility, metals are the shapeshifters of the elemental world. They give us the flexibility to mold raw materials into complex, functional machines. So, we have a strong, shiny iron bicycle ready to ride, but there is a catch. If you leave that brand new bike outside in the rain, it faces a natural enemy. Metals have a highly active chemical life. Most of them are desperate to react with the oxygen and water in the air. When iron does this, it corrodes, and that shiny frame is rapidly covered in rough, flaky orange rust. This chart, the reactivity series, ranks metals by their aggression. At the top, highly reactive wildcards like sodium and potassium literally explode in cold water. Down at the bottom, stable metals like silver and gold refuse to bond with oxygen, meaning they never rust. This is why you can find raw gold nuggets pulled straight out of the earth, perfectly preserved and shining after thousands of years. You might wonder why we don't just build rust-proof bicycles out of solid gold. Aside from the massive cost, gold is incredibly soft. A gold frame would warp and bend the moment you tried to pedal. This leaves builders looking at the middle of the reactivity series. We need elements like iron, which are strong and abundant, but we have to solve their rusting problem. To fix this, we change the structure of the metal itself by creating alloys. By melting a pure metal and mixing in a tiny fraction of another element, we can rewrite its physical properties. Take liquid iron and add a tiny amount of carbon. These small non-metal atoms act like cement, slotting perfectly into empty gaps between the iron atoms. This locks the grid together, creating steel, a material significantly harder and more rust-resistant than pure iron. Purifying and mixing these elements on an industrial scale requires massive heat and specialized converters to blast away the unwanted impurities. In other cases, we let the metal do the work. When copper reacts with the elements, it doesn't flake away like iron. It slowly turns green, creating a protective shield of its own that preserves the metal underneath. Ancient engineers mastered this kind of chemical protection early on. The iron pillar of Delhi was forged with such precise mixing that it has resisted rust for over 1,000 years. Building durable machines means we have to tame the elements, using chemistry to mix, match, and protect metals to fit the exact job we need them to do. The assembly of a bicycle frame coordinates different elemental groups to handle the stress of the road. The frame uses malleable steel alloys to hold your weight, while highly ductile copper wires stretch through the tubes to carry electricity to the headlight. But the bike wouldn't be rideable without the nonmetals. The rubber tires, the plastic seat, and the handlebar grips insulate you from the shock of the road and give the machine its flexibility. Concluding, warm. Modern engineering works because we don't choose between metals and nonmetals. we use their opposite personalities together. The next time you walk past a car, look down at a smartphone, or hop onto a bicycle, you aren't looking at random parts. You are seeing the periodic table in action.